Hello everyone, I'm Shouxi Luo from Southwest Jiaotong University. Today, I will share our recent work on Coflow scheduling. This is a joint work with Lin Zhifan, Huan Laixing from Southwest Jiaotong University, and Hongfang Yu from the University of Electronic Science and Technology of China. As outlined in this presentation, I will first overview the Coflow communication partners widely existing in modern data center networks, and introduce why those distributed applications call for data network Coflow scheduling. Then, I review the mostly related existing solutions and analyze why they fall short in the Coflow scheduling. After that, we will move to the two trade-offs that motivate our scheduling designs, and introduce how the proposed solution, Poco, achieves the design goals. In the end, I will briefly present the performance study of Poco. Okay, let's look into what Coflow is. In modern cloud data centers, distributed applications widely employ data parallel designs to achieve efficient large-scale data processing and analysis. In those systems, a job is split into multiple staged tasks, and those tasks are carried out by a group of machines. During the processing, involved servers triggered groups of parallel and collective flows to move the intermediate results from machines of the current stage to the next. Those flows in the same group share the same performance goal, and their compilations act as a barrier of the distributed computation. In many systems, with the increase of computation power, the network becomes the bottleneck of the entire system. To optimize the network for distributed applications, researchers have recently abstracted such a group of flows out as a Coflow, and suggested the underlying network to perform Coflow-aware traffic scheduling. In production, many distributed jobs are latency sensitive. Accordingly, to optimize their performance, the underlying network should complete the involved Coflows within deadlines. To optimize the completion of deadline-bounded Coflows, researchers have proposed many solutions. For example, in case the deadline requirements are hard, one can adapt admission controls to limit the number of active Coflows and guarantee their completions by controlling their sending rates. Indeed, this is exactly the design adopted by various. Besides hard deadlines, for some applications, the deadline requirements are soft, and the scheduling goal is to minimize the number of deadline missed Coflows. To achieve this goal, the best scheduling guideline is to let Coflows occupy the network, respecting their remaining time to deadlines. For example, the proposal of G2CAS follows this direction and is reported to achieve near optimal performance. Although those proposals can perform deadline over Coflow scheduling, they all overlook the tolerance of modern distributed application. Due to the approximate nature of the involved computation, many of today's distributed applications are able to tolerate incomplete data transmissions by design. For instance, in large-scale web search systems, for each cache-missed request, a group of back-end servers will report the aggregate the top-end results to generate the final response. A partial transmission is acceptable since it's a sample for the raw data thus still bringing benefits to the application. Likewise, during the distributed iterative training of deep models, many models are also robust to achieve comparable convergence rate over incomplete parameter updates. Actually, recent studies show that many machine learning algorithms are bounded loss tolerant. Their end-to-end job performance would get little impacts in case the loss of data is below a certain fraction. And for applications like coding-enabled distributed storage system on object arrays, because of the coding designs, obtaining any subset of data whose volume reaches the threshold should sufficient to serve the request. All above observations demonstrate the ubiquity of tolerance on incomplete inputs among distributed applications. Indeed, such a type of tolerance also brings new optimization space for the schedule of their time-sensitive coflows. For example, the recent work of Comiopic explored the tolerance of partial transmission by maximizing the marginal partial throughput of concurrent coflows. However, its design is inflexible and provides no performance guarantees to the application. Thus, the compilation of Coflow is unpredictable, limits its usage. As is known, the volume that flow can deliver in a time slot is determined by the integration of its allocated sending rate over time, which is restricted by the rate allocated to all other flows in turn. Those observations imply the fundamental design space and the flexibility for the schedule of Coflow. In a heavily loaded network, by taking advantage of the application's tolerance, we can trade the achieved completeness for shorter completion times, and we can trade one flow's completeness for those of others. Moreover, if the data delivered by a group of flows within a coflow is changeable, the network can balance the total task among all its subflows with respect to the link clouds. Based on those findings, we proposed Poco, a policy-based coflow scheduler to achieve customized coflow compilations for distributed applications. In short, Poco implements two key designs. At the high level, it provides a set of policy primitives with which distributed applications can precisely define the requirements on both the deadline and the completeness among with each coflow. At the low level, Poco translates these requirements into time-slotted linear constraints and formulate a linear program to solve. Such a linear program explores the aforementioned trade-offs explicitly. To provide guaranteed performance to distributed application, Poco implements admission controls. Specifically, when a coflow request arrives, Poco builds a linear program to check whether there is the rate scheduling that could admit this new request without sacrificing the requirements of all admitted coflows. If so, any feasible result of the linear program is a bandwidth allocation to admit this new request. Otherwise, this new request would be rejected. Following such a design, the remaining challenge is how to solve those large-scale linear programs efficiently. The solution of Poco is to parallelize the involved computation by limiting the specific structure of the linear programs. Next, let's move to how the parallelization works. As we have shown, to handle a request, the core of Poco is to solve linear programs. For this linear program, we can rewrite it into its metric format. According to the theory of linear optimization, such a problem is proven to be solvable in polynomial time. Currently, the best practice is to leverage interior point method to solve. Basically, interior point method solves the problem with iterative designs, in which the core of each iteration is to solve such a linear equation system for a given right-hand side vector V. Obviously, the left-hand side matrix in this linear system is positive sim-definite, having a Coflow decomposition in most cases. Accordingly, the original problem can be solved using the Coflow efficiently. Also note that in case if the matrix is not positive definite, the equation can be solved with other approximate methods as well. The key optimization adapted Poco solver is to accelerate the solving by leveraging the space structure of the constraint matrix. We find that the constraint matrix of the linear program follows the block angle structure as this slide shows. Basically, the matrix is made up of two types of building blocks. The building block of AI specifies the amount of data that the ith Coflow should complete with its deadline, along with its subflow's volume limits. Likewise, the building block of BI specifies the constraint of link capacities involved by the ith Coflow. By looking into the details of AI's building blocks, we also find that the same block angle structure is repeated. Also note that as the DK is a diagonal metric, it's easy to verify that the Coflow decomposition always keeps the same block angle form. Accordingly, to be consistent with the structure of the constraint matrix A, we labeled its subblocks as L's and M's respectively. Note that after the matrix multiplication, those building blocks at the same location should be equal. This observation gives us a way to compute the value of the building blocks of the matrix L efficiently. As the figure on the right side of the slide shows, for building blocks except the one at the right bottom in matrix L, their computations can be carried out in parallel. Once we obtain the value of matrix L, we can further obtain the value of vector dy for the given right-hand side vector V. Such design not only explores the sparsity of the constraint max, but also makes the computation parallelized. We made a simplified implementation of Poco server on CPy to demote the performance gain. We use the parallelized solver to solve randomly generated constraints and right-hand side vectors, and compare the time cost with those of the straightforward implementation. As the results show, the Poco server obtains huge performance gains by making use of block angle structure of the constraint matrix. Basically, The speed up grows almost linearly with both the size and amount of involved constraint blocks. Besides the benefits of parallelization, we also set up more tests to study the scaling ability of Poco. Basically, we add both completeness and deadline requirements to the Facebook Coflow traces to drive the tests. We build a flow-level simulator in Python to perform detailed replays of the aforementioned Coflow traces. As the results show, without doubt, by explicitly deploying the tolerance of incomplete Coflow completions in scheduling, Poco would admit almost all the Coflow requests and guarantee their QoS requirements. Results also confirm the flexibility of Poco. In summary, in this paper, we designed Poco to achieve policy-based selective Coflow compilations for deadline-sensitive applications. More details refer to our paper, and please join our Slack discussion or drop me emails. Thank you for watching.